In my opinion, capacitors are fairly easy and intuitive to understand and use, but inductors not nearly so much. They are a fundamental component, and you see them all over the place, especially whenever you're dealing with power supplies. But they're definitely not as easy and intuitive. I consider them a step 2 learning component rather than step 1. So I was struggling to learn inductors, but as soon as I started taking inductors and comparing and contrasting their similarities to and differences from capacitors, all of a sudden it just started to click for me, and I realized how incredibly similar these devices really are. The unit of capacitance, the farad, and the unit of inductance, the Henry, mathematically they are almost the reciprocals of each other. And capacitors and inductors are almost the reciprocals of each other as well. So this is the way I've chosen to learn and teach inductors, and the comparison itself is also instructive. So let's get to it. Both a capacitor and an inductor are short-term energy storage devices, where a battery would be a long-term storage device for energy. They both will hold little bits of energy in one form or another and then release it. They'll hold it quickly and release it quickly, and we can use them to implement interesting things like filters and timers. But fundamentally, they're energy storage devices. A capacitor stores energy as charge, as in an imbalance of electrons, which is what electricity is anyway, or rather what voltage is anyway. And the symbol for a capacitor basically includes its conceptual construction. You can build a capacitor like this, and there's also more complex spiral ones with multiple flanges and so forth, but basically you have two conductors separated by a gap. Anywhere you have two conductors and a gap between them, that's a capacitor. You apply a voltage, electrons go in and start stacking up on one side. The electrons on the other side get pulled away as well as shoved away, and you get a charge imbalance. When the voltage is higher than whatever the capacitor is charged to, the capacitor charges more. When the voltage is lower, it discharges, so it wants to always stay the same voltage. And this is why capacitors are described as devices that resist changes in voltage, because anytime there's a change in voltage, the capacitor is going to try and take as much power as it possibly can to fix that imbalance. So if the voltage goes up higher than the charge, it's going to suck down all the extra power trying to charge up, and after the capacitor is only going to see that already amount of voltage it had. And the same for discharging. When the voltage goes down, the capacitor starts dumping it, and after the capacitor still sees the higher voltage because the capacitor is providing it. Capacitance, in farads, is basically the capacity of the capacitor. As in, let's say, conceptually, 1 volt is this much of a layer of electrons. So you have a layer this thick, like icing on a cake of electrons. Again, conceptually, this is not a physics channel. So this might be 1 volt, and this might be 2, and this might be 3. So your capacitance would be how many electrons per volt, fundamentally, would stay there to make that amount of charge. If you increase the capacitance by increasing the surface area, then the same thickness layer would have more electrons in it to give the same charge. And if you shrink the capacitance by shrinking the surface area, then the same thing happens. And then you can shrink the dielectric and do all this other stuff. But basically it's just capacitance is how much charge, how much buildup of electrons per unit of potential difference, the volt, is in there. So more capacitance presumably means more time to charge. So let's switch to inductors for a moment. An inductor is just a coil of wire. We've seen that. There's your symbol. Electromagnet, solenoid, transformer, inductor, all these things are basically just coils of wire arranged in different ways, and the name is based on the context. When we say inductor, we mean just a single coil of wire. It could be a tiny one inside a little resistor looking thing. It could be a big one with this big old coil. It could be half of a transformer. It could be all kinds of things. But we're talking about just a single coil of wire. And you can have them next to each other doing various things, but, that's configuring circuits and stuff. When we're talking about an inductor, it's just one coil. And we've gone over electromagnets. We know that when you put a current through a coil of wire, you get a magnetic field. An electron has an electric field. Electricity is electrons moving in aggregate. So electricity is an electric field moving in aggregate. A moving electric field is a magnetic field. So you put current to an inductor, you get a magnetic field. So instead of storing energy as charge, it stores energy as a magnetic field. What is the strength of the magnetic field proportional to? It's proportional to current, because the electrons, the moving electrons, and their electric fields is what's creating the magnetic field. If the current is steady, then the magnetic field is steady. If you increase the current, the magnetic field gets stronger. If you decrease the current, the magnetic field gets weaker. So energy is stored in the form of a magnetic field, and this is why the inductor is described as a device that resists change in current. If you increase the current going through an inductor, then it's going to consume the excess energy to increase the strength of the magnetic field, and it's actually going to oppose the actual increase of the current. It's going to take the excess power trying to push the current, but it's not actually going to let the current be pushed until the magnetic field gets stronger. And the same thing when the current goes down, the magnetic field begins to collapse because the current isn't enough to sustain it anymore, and it starts putting out current. This is the flyback diode and all that stuff. It starts putting out current, or forcing more current through, to counteract the lower actual current going through it until the magnetic field weakens. Think of it in terms of inertia. If you have a wrecking ball on a chain, this big old wrecking ball, and you try to push it, it's going to be really difficult to do. It's going to feel like the wrecking ball is pushing back against you, but it's actually not. There's no rockets on the other side. It's not a living thing acting against you. There is technically no force being exerted by the ball on you. The inertia is called an opposing force, but it's not a force the same way like me lifting this pen, moving this pen around, I'm exerting force on this pen, exerting energy to exert this force. Inertia is not energy being expended. There's not energy being drained from the magnetic field to impose this force. It's inertia. There's not energy being drained from the wrecking ball to actually create an energetic force against you. It's just inertia. It's just a property of the universe. You are expending energy, and in doing so, you're putting energy into the wrecking ball. You're taking energy out of yourself and putting it in the wrecking ball, putting it into the system is what it's called, and so the wrecking ball begins to move slowly. And if you're trying to move the wrecking ball at a certain rate, like you have a certain maximum speed in mind, you want to push it so fast, the closer it gets to that speed, the less force you have to exert. And once it gets to that speed, you're not exerting any force. Forget gravity for a second. Just pretend you're pushing it horizontally. You're not having to exert any force to push it because inertia is now working with you. So that's kind of how an inductor works. So you have your wire, you have your inductor hooked up to the wire. Of course, that's, let's do it like this. So your voltage is an EMF, electromotive force. Electricity, motive, motion, force, the force. Electromotive force is the force moving electrons. I sounded like a chubby emu, didn't I? So voltage is an EMF. It causes electrons in aggregate to move in one direction. When you have increased the current, when the current has gone up, or you're trying to, so you've increased the voltage, because that's how you increase the current, you increase the voltage. So higher voltage is trying to push higher current. So each electron is being pushed harder, and as a result, more of them should go through in a unit time. That's increased current. But the magnetic field here is based on the current going through. So you've increased the current. The magnetic field is not strong enough yet. And according to Lenz's law and fancy physics, there is what's called a back EMF. It opposes the current with an EMF in the other direction. There's a voltage. You have whatever voltage going across the inductor. And then you have the inductor generating a voltage. Again, not by expending energy. It's inertia. This voltage is technically not real. It is real, but conceptually, it's not real. It's just like the wrecking ball is pushing against you, according to Newton's laws, but not technically because it's not using energy to do it. Conceptually, it's just inertia. It's the same here. The magnetic field is not being drained to push against you. The magnetic field pushing against you is a consequence of inertia. So the current is going to stay the same, but the increased voltage, the increased force of pushing, is going to push against this counter EMF. And in doing so, it will strengthen the magnetic field. That extra is going to make the magnetic field stronger. A stronger magnetic field is proportional to a greater current. So now it's going to resist the flow less. The back EMF is going to be smaller because the field is stronger. So the current will go up, but it's still pushing. The voltage, it wants to make the current higher. So it keeps pushing and pushing and pushing, just like you pushing the wrecking ball. The magnetic field strengthens as the voltage is pushing harder than it needs to for the current. And as the field strengthens, this back EMF shrinks and shrinks until the voltage is successfully putting across the current it wants to put across, which matches the strength of the magnetic field, and there's no more back EMF. And in the same way, if you're trying to slow down the wrecking ball is swinging back at your face, and you go, stop, and the wrecking ball says, ugh, and now you're bleeding, but you have successfully removed some energy from the wrecking ball and put it into your face. In the same way, when you have your voltage trying to put across current, and the current is going down, the voltage is weaker, and the current that voltage would cause is lower than the current proportional to the existing magnetic field strength. Now you get a forward EMF that's technically helping you, assuming you didn't put a backwards voltage, but basically just the current goes down. So now the magnetic field is trying to collapse and get weaker. So it's exactly the same thing. The current gone down is not providing enough oomph to keep the magnetic field at the strength it was, so the magnetic field is going to collapse down to the strength that this voltage will support. So in the process of collapsing, that energy which had been stored in the form of the magnetic field comes back out that way. It resists the flow when it's trying to be increased, and it aids the flow when it's trying to be decreased. The same as the wrecking ball. Inertia resists you trying to add energy to the system, and the process of trying to remove energy from the system is to basically just work against it instead of it working against you. Now, unlike the wrecking ball, you don't have to apply a backwards current to stop the inductor. It's not physical inertia. It's just an analogy. Basically, it'll just charge or discharge, strengthen or collapse to whatever the standby current is, the stable, stationary current is. So that's how an inductor works, and that's why it's said to oppose a change in current, because it literally does with its inertia. It provides current when it's discharging, and it takes the power away when it's charging. So that's the fundamental mechanism. And in terms of the unit, we usually see L for inductance, and the unit is the Henry, and you can have a millihenry or microhenry or whatever. Oh, I don't know why it's L. I haven't thought to look it up. But you usually see LRC is inductance, resistance, capacitance. It's just an L. So an LR circuit is a simple filter. So you have your coil. Inductance, once again, is a measure of the capacity, just like a farad is for charge. If your inductance is higher, then for the same amount of current, not voltage, but current, for the same amount of current, the magnetic field is basically going to be stronger. For 1 amp, 2 amp, 3 amp, you're going to have more magnetic strength in there for the same current. If you make it longer, the inductance goes down. If you add coils, the inductance goes up. And if you make it thicker, the inductance goes up. For physical reasons, let's not get into that. But basically, both capacitance and inductance, farads and henrys, are the capacity of input, as in voltage or current, to energy stored. Farads for a capacitor, henrys for an inductor. Now let's start getting into some of the cool parallels to actually understand the behavior of these things and why I think they're really sister devices. Do you remember this? Tau, that's pi. I think I do that every time. Tau equals R times C. Resistance times capacitance is called the RC constant. This is when you're trying to do timing. We say that R times C is approximately 63% charge. If the capacitor is empty, it's 63% charge up to full. If the capacitor is full, it's 63% discharge down to empty. 63% roughly, and that's the time in seconds. So tau is in seconds. So R times C is the amount of time it takes to roughly get 63% charge from empty. And we can use that to make filters and such. And the charging curve is like that. and the discharging curve is like that, and there's the shape of it. Where does this come from? When you are charging a capacitor, the voltage on the capacitor equals the voltage of the source, we'll just say B for battery, times 1 minus e to the negative t divided by R times C. Let's go a piece at a time. Don't worry, I'm not going to do crazy math. Let me just explain what this is. T is time. 0, T equals 0, is you just put the voltage on. The capacitor is discharged. It's the start of time. So time in seconds goes up. You're just how much time has elapsed as the capacitor is charging. So we have a proportion here. This E thing, this whole thing goes from 0 to 1. I'm going to say that now. This right here goes from 0 to 1. So at the beginning of time, you have VB times 0. So the voltage is 0. The capacitor is fully discharged. At some time, infinity, you have VB times 1. So the capacitor is fully charged. Now, before I explain why E is in here or anything, let me just say, what if time is RC? What if T equals R times C? Well, T equals R times C, so R times C over R times C is 1. So this is e to the negative 1. E to the negative 1 is approximately equal to 0.36, so 36%. 1 minus is approximately equal to 0.63 or 63%. Gee, does that sound familiar? That's where that comes from. At R times C, this whole thing works out to be the voltage being applied times about 63%. It's like magic. That's why they chose 63%, because the math is easy. What do you get at 5 times R times C? Time equals. It's commonly said that 5 RC time constants means that the capacitor is fully charged. It's approximately equal to 99%. Once you do this, it ends up being e to the minus 5, 1 minus that, and you get about 99%. So we just, in the electronics world, say good enough. And in the engineering world, they say it's within tolerance. So there's complex fundamental electronics, physics, blah, 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 that derives this. E is one of those magical constants. Anytime you see a formula that's got a pi or an e in it, you know that you're working with the really cool stuff, the really fundamental natural world stuff. Have you ever wanted to make a mathematician spontaneously orgasm? Just say 1 plus e to the I pi, and then open your umbrella. So you see that e and you know good things are happening. But basically 1 minus e to this is just something that starts at 0 and then eventually goes to 1 at infinity. And that's where RC comes in. That's just how the math works. They chose RC to be the number that everybody talks about because the math is just so pretty. And they said, all right, it's about 63%, that's RC. An inductor, it has a tau as well. It's L over R. Remember that L is the inductance in henries? So if you multiply farads by ohms, you get seconds. If you divide henries by ohms, you get seconds. You get a glimpse now. You get a glimpse of, hey, wait, that's pretty cool. Yeah? So what does this mean? Let's say the voltage of the inductor, as in the voltage drop, the back EMF, the EMF that's fighting, because the inductor is fully empty, just like the capacitor. The inductor is empty, so we're going to apply some voltage to it, which means we're going to apply some current to it. The magnetic field does not exist currently. So the voltage drop, the fighting against the voltage, is voltage of the battery times e to the negative t times r over c. Let me write this like this. Negative t times r over L. I think I wrote C. You get the idea. It was supposed to be an L. So, once again, e to the negative, and so if t is 0 at the beginning, at time 0, this is 0, so e to the 0, anything to the 0 is 1, so at time 0, the voltage across the inductor equals the full voltage. Basically, when there has been no magnetic field developed at all, and you apply a voltage, it's going to completely counteract that voltage because the magnetic field corresponds to a current of 0. And then, at infinity, e to the negative infinity ends up being 0, so VL equals 0. At t goes to infinity, VL equals 0. So e to the minus whatever is doing the same thing for the capacitor and inductor. So what happens at tau equals L over R? Well, L over R and R over L cancels to 1, so you've got e to the minus 1 again. So that equals about 36%. So the inductor has charged to about 63%, and 36 is about left over from 63. So the back EMF started at 100% and it has gone down by 63%. The back EMF has been reduced by 63% that same time constant. And so they say, once again, that 5 times L over R is about 99%, I can write, of the way charged. And once again, you're going to see this in other forms, and you won't see, if you look this up, you won't see this as a voltage, you'll see this as a current. I just divide it over so it's voltage. The point is to talk about the back EMF. This is the formula for the back EMF. So we trust the smart people to have applied Lenz's law and all this other stuff to get this formula correct. I'm simply showing you this e to the minus t and whatever, which is your tau, shows up in both the capacitor and the inductor, which is why you have the same kind of time constant, the same kind of curve, and you can use both of them in the same kind of way. So what happens if you put capacitors in series? If you just have a capacitor and so forth in series. Let's say series and parallel here. That's an R, or is trying to be. 1 over the new capacitance, or the combined capacitance, is the sum, let's just do it simpler. I won't use the fancy math notation, we'll just say 1 over C1 plus 1 over C2, and so forth. Now you may remember this kind of math from the resistors. Resistors in series is just you add them, and then resistors in parallel you reciprocate them all and add them and then reciprocate again. Same math, different thing. In parallel, when you have a rail and a capacitor across it, and then another one like this, in parallel, the parallel capacitance, and I'm not going to derive it, this is not a physics course, once again, we're trusting the smart people, you just have the new capacitance is C1 plus C2. For an inductor, guess what? It's the opposite. The new inductance for series is L1 plus L2. For parallel is 1 over L1 plus 1 over L2. Inductors in series and capacitors in parallel just add their capacity. Inductors in parallel and capacitors in series also add, but they do it by this fancier formula. How do we conceptualize this? For a capacitor, think about surface area. If you have two capacitors in parallel, you could kind of think of just sticking their surface areas together and you get double the surface area, assuming they're, don't get into the physics, just the analogy. I'm just explaining. But conceptually, you can think in parallel, you're just kind of adding their surface areas together. So that would just increase the capacity very simply. Whereas if they're in series, you've got, electrons being pushed. Let's say your voltage is like this, so negative voltage over here. So electrons are being pushed this way and they're being pulled this way, but in between them, they're being pushed from one to the other, and there's a complex interaction there, so it doesn't quite just add up. What about an inductor? Let's say you have an inductor and another inductor. So you put a certain voltage across this inductor and you're trying to charge it up, and there's going to be an EMF from the battery and a back EMF from the charging process. Well, instead of that, let's say you have the voltage across both of them. So you've got your EMF way across here, and they're each going to try and put a back EMF like this. So it's kind of like batteries in series. This is generating a back EMF, which is kind of like having a little battery pointed the other way, and so is this. So the batteries are kind of in series, and so the back EMF back voltages are adding together. And in parallel, if you have your inductors in parallel, the best I can say to you here is just, it's complex. So you have your regular EMF here, but then you've got your back EMFs like this, and then it's like having batteries here and do your Kirchhoffs and ick. The point is just, it's more complicated. Now, I'm sure that was absolutely nothing like the actual physics involved. I don't care. The point is just to intuit it. The point is to be able to understand it without having to fuss about it. And then, if you want more, go take a physics course. So what is a capacitor low-pass filter? Well, you have your resistor, and then your capacitor, and here's your output. You measure your voltage drop across the capacitor, that's your output voltage, and then R times C is your timing. That's a low-pass filter. What's a low-pass filter with an inductor? Well, you have an inductor, and then you have a resistor, and here's your output. The capacitor is in parallel, the inductor is in series, and you get the low-pass filter. So your square wave becomes a triangle wave, and that characteristic shape, you may recall like this, and then like this, and then like this, and then like this. They both produce it because the charging and discharging curves, remember how it was just a voltage multiplied by e to the negative t times whatever, times your time? They both do the same thing, you just hook them up backwards. If you have a high-pass filter, you have a capacitor in series, a resistor in parallel, there's your out measured across the resistor. If you have an inductor, then you have your resistor, your inductor, there's your out. Capacitor in series, inductor in parallel is a high-pass filter. It's just the opposite, and that's really cool. I cannot stress to you how cool this is to me. Now, you're going to usually find filters made out of capacitors rather than inductors. First of all, because they're easier to understand. Second, because they're more compact. You can get a capacitor a whole lot smaller than you can get an inductor. And third, they're a little better behaved, as evidenced by me hooking up inductors to my oscilloscope. Capacitors give nice, beautiful, easy to grasp voltage curves, and inductors give the correct curves, but the oscilloscope reads them as fairly wiggly and noisy. I'm sure improving the quality of my inductors would help there. I've actually ordered a box of really good ones, because right now I'm using a homemade inductor and it's not perfect, let's just say. But the point is, they're backwards from each other, just like this. And there's one more thing. You remember reactance? When we're talking about a filter with a capacitor acts as if it's a variable resistor. If you have frequency of a signal and you have reactance. Now, resistance, impedance, and reactance are all just ohms. The name comes from the context. Resistance means actually a resistor, or the resistance in a wire or something, like physically resistance. Impedance is usually talking about inputs and outputs, effective resistance there, and reactance is usually talking about a passive component acting as a variable resistor in this way. But here's the curve. A capacitor, remember we talk about how it blocks DC and passes AC. As the frequency goes down, and DC is frequency 0, a sine wave is frequency 1, it blocks more. So your frequency 0 would be infinite impedance, not really, but you get the point. And then your sine would be down here, and then as you get more and more of a high frequency noise, you have a capacitor that's just letting it through. It's acting as less of a resistor for that frequency, and then you get your Fourier split and all that stuff. So a capacitor has greater reactance, which is usually written as XC. The reactance, because they wanted to write X, I don't know. Reactance of the capacitor equals 1 over 2 times pi times frequency times the capacitance. As the frequency gets bigger, the denominator gets smaller, which means the reactance, the effective ohms, this is ohms, gets smaller. Higher frequencies, less resistance. Until you get crazy high frequencies, don't just normal frequency ranges. If you get stupidly high frequencies, you need special capacitors and whatever because they start to act funky. But, you know, when we're talking about the human range of hearing, processing normal signals, this is your formula. Higher frequency, less reactance. Here's your formula for an inductor. The reactance of an inductor is 2 times pi times frequency times your inductance. It has the opposite curve. An inductor, if you have frequency and reactance, it actually goes up. Once again, it's the counterpart to a capacitor. The slower the frequency of the original wave, of the original waveform coming in, signal. See, the inductor, okay, so the signal is going to change the current back and forth, up and down, and the inductor is going to resist that as it charges. But if you have a slow frequency signal, it's always going to have time to charge and discharge before your signal is changing too much. So the slower the signal, the more the inductor is just going to delay it. It's going to delay the signal, it's going to shift it, phase shift, but your signal is not really going to change much because it's got plenty of time to resist the flow of current, resist the increased flow of current, or counteract the decreased flow of current. Magnetic field strength changes and it stabilizes again. The faster the frequency, the less time you're giving it. So if you have a really high frequency signal, then it's going to spend the vast majority of its time giving you strong back EMFs to oppose an increase or putting out strong current when the field is collapsing and it's charging and collapsing really, really fast, and it never gives it time to really let the signal through. So the higher the frequency, the more the inductor is going to not let the signal through, but if it's real low, it'll let it all through. A DC signal, the current is not changing. So for DC, If the frequency is 0, the reactance is 0. Whereas here, if the frequency is 0, take your limit, because you can't divide by 0, but if you take the limit, the reactance is infinite. But here, frequency 0 just means 0 reactance in the ideal situation. So if you put a DC signal across an inductor, it'll just go across. An inductor does have a resistance, an impedance, whatever, inside it. The usual inductor is going to have maybe 1 ohm to 100 ohms-ish. I'll do a future video on this. So there's going to be a small resistance, a small impedance, whatever, even with a DC signal, but small. For the most part, it's this. And look, it's just the upside down with the L instead of the C, and that's really cool. Isn't that really freaking cool? This is how you understand an inductor and a capacitor, or you try to anyway. Took me a while, and some of it, a good bit of it, I still kind of say, okay, the very smart people know what they're talking about. But everything about a capacitor and an inductor is just the reverse, the inverse, the counter of the other. They do the same thing in different ways, and that's amazing to me because you've got, electrons being stored across a little gap, a dielectric gap, versus a magnetic field being charged and discharged by current. They're completely different things. The only commonality is it's electrons in there, and yet fundamentally they're so very similar. I love it. I hope you do too. And this is one of those videos where I could definitely have explained this poorly, because I've gone for weeks and learned this and try and figure out a way to explain it to everyone else. So if I have explained something poorly or not enough, or made mistakes, let me know in the comments. I can always make an additional video. I can always fix this video, whatever you happen to need. So while you digest this information overload, I'll be seeing you.